Bam! Mr. Tarrou. In this math lesson, we're going to look at three forms of equations that describe a three-dimensional plane. We're going to look at a little diagram here to kind of see all the geometry that's going on, and we're going to have an example where I'm going to give you 3 points in a plane, and we're going to find the vector form of that equation, the parametric form, and then move into the Cartesian form, and that'll be the end of our lesson. Now, I'm building up a pretty big playlist of math lessons that deal with vectors, so you can find a link to the playlist in the description. So vector and equations of planes. A plane pi is defined when one of its points with a position vector A and two non-collinear vectors, we're going to call this vector u and vector v, are parallel to the plane. So we don't actually have to know multiple points that are within our plane. We really only have to know one point with a position vector of A. But we do then have to have two collinear vectors that may be in the plane, or they're just simply necessary that they're parallel to the plane. And the vector form of that equation is vector r, or vector form of our plane equation is equal to vector a plus alpha times vector u plus beta times vector v. And what the heck does all this mean and represent? Well, you're obviously studying vectors if you're watching this video, and you might recognize the first few terms of this equation, the vector form for the equation of a line. But when you have a plane, like, let's say our three-ring binder is one sort of directional vector, and inside this folder we've got all kinds of different planes, and we can have these planes, which are the individual pieces of paper, they can move around because they're swinging on the three rings of our folder. So having one directional vector is not enough like it is with a line. You need two. So we have our plane pi here drawn in white on our three-dimensional axis of our z, x, and y axis. We have this point A, which has the position vector, where we're referencing the position vector starting off of the origin. So we have vector basically OA, only we're writing it as just vector A. OA is heading off to that point. The one point that we have to know lies within the plane. And we're going to be able to describe every other point in this plane pi with basically vector R. Vector R is showing us or giving us a position vector for every other point that's in the plane. And we have these other two vectors of vector u and vector v, which in the diagram looks like it's on the plane, and maybe it is, but it certainly needs to be parallel to the plane that we're going to write the equation for. And these two non-collinear vectors are really kind of giving you that sort of, going all the way back into geometry, where 3 points define a plane. We've got an initial point, which these two vectors may or may not necessarily share, but just for convenience and simplicity, let's say the vector u and v are positioned to share that same initial point. And of course we have the terminal points that each of these two non-collinear vectors have. Well, that's going to be 3 points to find a plane, just like all the way back in geometry. And not define the plane per se, because our non-collinear vectors may not actually be in the plane, but they're defining a plane that's parallel to the equation of the plane pi that we're going to find. And, you know, if I have this plane in this particular direction in space, and it can be anywhere, but no, it can't. It has to have one point. So we're going to know, based on these two non-collinear vectors, what's the direction of that plane, what's the orientation, if you will, and then we're going to have that one sort of initial or given point that lies in the plane, and that's going to lock that plane in space and just have that one sort of unique plane, if you will. So if we know a point with the position vector A, two non-collinear parallel vectors, or they may be in the plane as well, we got an equation that defines that plane. Now, vector r is equal to vector a plus alpha vector u is our vector form for the equation of a line. And like I just said, but we're just going to expand that into another dimension and have the vector form for a plane. Okay, so, and before we move on to the example here, while I'm drawing this off to the side as identifying those directional vectors, again, making the orientation of that plane, of course, we have this initial point, and these two vectors are defining where every other point is in the plane from vector A. Well, if I just move these around, because vectors are defined by direction and magnitude, not by initial point, and we have scalar multiples on our vectors in our vector form for the equation of a plane, I could say, well, maybe we need to make vector u maybe a little bit shorter, but in that same direction, reduce it with a little scalar multiple. And add that through that triangular method of adding vectors we talked about in an earlier lesson. We might need to shorten up v a little bit, but from point A with a position vector of vector A, we can move some multiple of u and add that with some multiple of this other non-collinear directional vector, basically, the directional vector for the plane, and we can define every other point on the plane. That's what's going on, and our first example is coming up right now. Man, I got so excited about doing the example, I forgot to show you how to convert between these three forms. If you're really good with your vector, parametric, and Cartesian form for the equation of a line, actually, you kind of already know how to do this. We can remember that this is a position vector for any point on the plane. That vector A is our position vector for our initial point. Our directional vector u, and then plus, so that's alpha times the vector u sub 1, u sub 2, u sub 3, our vector written in column format, and then beta times vector v. Okay, so writing out sort of these vectors in that column vector format, the first two position vectors, and u and v are directional vectors, just go along the rows here, and remembering, of course, that these scalar multiples go to each of these three components for each of these two directional vectors, and we get x is equal to x sub 1 plus alpha times u sub 1 plus beta times v sub 1. And I'll just be quiet and write the next two rows, since I can't write and talk at the same time very well tonight. And that's all there is to converting from vector form into parametric form, where we're tracking the x and y and z coordinates of our three-dimensional point individually with our scalar multiples of alpha and beta acting on those two directional vectors. But whatever you need to do to eliminate the parameter of alpha and beta, we're going to do that with the third part of this example. We're going to have a times x plus b times y plus c times z is equal to d. And let me just double check that okay. So we're going to solve a system of equations with three variables and three unknowns to get it into Cartesian form, and that's what you're about to see right now. So we have given the points that A has the coordinate of -1, 0, and 2, B has the coordinate of 3, 1, and 1, and C has the coordinate of 3, 0, and -1. Find the equation of the plane ABC in all three forms. Now I'm not going to try and certainly draw a three-dimensional plane with the 3 points and rotate it around. I don't have, well, I have a flat chalkboard, but so this is not drawn to scale, but just imagine that we have some plane. Somewhere there's a point A, B, and C, and remembering the conditions that we just went over, we need two non-collinear vectors in or parallel to the plane and one given point. Well, we're going to pick one of these 3 points, and just because it's in alphabetical order, I'm going to say A, and we're going to find vector AB, we're going to find vector AC, that's going to be our two non-collinear directional vectors. And you can make these vectors in any format. You can pick any one of these three coordinates to be your initial point or your known point that's in the plane. But that's all we need to write the vector form for the equation of this plane. So we're going to find vector AB, and this time try not to make a sign error because I'm recording this for a second time. I didn't have my live students telling me that I made a sign error, but we have 3 minus negative 1. I rely on them a lot in my classroom. 1 minus 0. I really just make mistakes, make sure they're paying attention. Right. 1 minus 2. Terminal point minus initial point. And we have 4, 1, and negative 1. There's vector AB. Now vector AC. Just using that same initial point for convenience because we're told all three of these points are in the plane. Terminal minus initial, 3 minus negative 1. 0 minus 0. 1 minus 2. Negative 1 minus 2. Let's not make the same mistake twice. We have 3 minus negative 1 is 4, 0, and then finally negative 3. And just because I don't want to record this again, yes, we are good. So we're going to let our initial point be vector A. So we're going to describe coordinate A with a position vector OA, or as my notes called it, lowercase vector a. And we have the vector, the equation of this plane ABC in vector format is vector r. The position vector for any coordinate r that's in the plane is equal to your initial point, or your one point that you know is in the plane. All of these are in the plane. We're going to use A, so negative 1, 0, and 2. And then from that point A, we're going to coordinate A, position vector A. We're going to move some kind of triangular addition method process, like you may have seen that I added to the page of notes just before I switched to this screen, just in case you didn't. We're going to go from that initial point described by this position vector through an addition process. Really, you could say it could be parallelogram method as well, but sort of a triangular addition process of adding those two vectors plus alpha times one of our position vectors. The note said vector u and v. We're using vector AB, so 4, 1, and negative 1, and some scalar multiple with the other directional vector. Vector AC, 4, 0, negative 3. And that's all there is to writing the equation of a plane in vector format. If you want to write this in parametric format, that you do need to go through, if you're going to write this, well, maybe you don't have to. We're going to show you that another process of going into Cartesian form in our next video. But one way to get into Cartesian format is to go through the parametric form or systems of equations for our equation here. So we're going to write vector r as that xy coordinate of any point on the plane, x, y, z. Go across each of those rows, remembering that these are scalar multiples, so they go to each of the components. X is equal to negative 1 plus 4 alpha plus 4 beta. Y is equal to, well, 0 and another 0 on the beta, so really we just have y is equal to alpha, 1 alpha. Nobody would really want to write that 1. And z is equal to 2 plus, nope, negative alpha minus 3 beta. And here is a system of 3 parametric equations describing plane ABC. Now, how to go from parametric form into Cartesian form? That clean little ax plus by plus cz is equal to d. Well, you do that through, no, I didn't make an incredibly hard system of equations here because we just have a simple y equals alpha. But you're going to bring this together. I generally do a lot of this with adding, maybe say the first and second, and then the second and third equation of this system, and create a system of two equations that has one of these variables. Maybe we take out the parameter of alpha first, and then we have just left two equations with two unknowns. Well, actually, you could argue, I guess it would be sort of three, but maybe you eliminate the alphas and you have a system of equations. You just have betas left, and then maybe do some kind of addition of those two equations and set it up in such a way that when you add, the betas cancel out. But we don't have a beta in the second equation, so I'm kind of just talking, and maybe just finish this example. As clean as this is coming out, what we're going to do is, let's go ahead and take, with these two equations here, and create through substitution one equation that eliminates the variable of alpha, and that's going to be through substitution. Remember, we were trying to eliminate alpha and beta, so we're going to take alpha out and plug in y. Cool. Well, now I have combined these two to be this equation, and we also have now this last equation, which I'm going to erase this in a second because it's really kind of technically in my way. I'm just writing it for teaching purposes. We're still going to use this a little bit for substitution because, again, the alpha is equal to y. We're going to do that substitution down here as well. But if we can now bring these together through, well, we could do that. I could write this as beta equals a lot of stuff and then plug it in to here. And then we're also going to use the substitution that alpha is equal to y. That's actually how my notes are written. I do this through substitution, but I can also say, you know what, we're going to take this alpha equals y, replace alpha here with y, and alpha here with y. And I think this is going to work out a little bit cleaner. I now want to add these two equations together after creating a set of opposite coefficients in front of beta, so that when I add these equations, the beta variable falls out, or that parameter, if you will, and we have just an equation with x, y's, and z's. So we're going to multiply this equation by 3 all the way through, and this equation by 4. And after we've multiplied the first equation by 3 and the second equation by 4, we have beta has opposite coefficients of positive 12 and negative 12. If we now combine these equations with addition, we have 3x plus 4z on the left-hand side. We have negative 3 plus 8 is 5. We've got 12 plus a negative 4 is 8y. And of course, our positive 12 beta and our negative 12 beta are going to cancel, giving us 0 as we add these. And wow, I'm glad I thought about this as I recorded this last part of the example, because it does come out to be cleaner than doing substitution. We're going to move the 8y over with subtraction, and we have 3x minus 8y plus 4z is equal to 5. Yes, indeed, there are always, especially at this level of complexity in mathematics, multiple ways of seeing your way through the problem, which makes all of this work really interesting. This particular system of equations was not terribly difficult to eliminate the parameters of alpha and beta. And by the way, let's just make sure, yes, before I call it a day, that this is correct. If you want a process for going from the vector form for the equation of a plane straight into Cartesian form and not having to go through the process of going through the parametric form and solving a system of equations, you can use another fourth form for the equation of a plane, which is still a form of a vector form for the equation of a plane, but it involves the dot product and a normal vector, which, well, is what the next video is about. So if you want to learn some more about vectors and equations of planes, check out my playlist in the description. I'll see you later. I'm Mr. True. Bam! Go do your homework.